Ever wondered how Netflix can stream to millions of users at once without crashing? Or how Amazon can handle millions of shopping carts during a flash sale? The secret isn't just powerful servers, it's a revolutionary approach to data called NoSQL. For decades, the relational database, with its structured tables and powerful SQL language, was king. But the explosion of the internet, big data and real-time applications created problems that the old king just couldn't solve. This led to a movement that started as a small rebellion and grew into an architectural revolution. In this video we are going deep. We'll cover what NoSQL actually is, how it's fundamentally different from SQL, the theoretical principles that govern it, the 4 major types you need to know, and where this entire field is heading next. By the end, you'll understand why the mantra for modern data is not only SQL. Part 1: The genesis of NoSQL. So, what does NoSQL even mean? You might be surprised to learn that its meaning has changed dramatically over time. The first use of the term was way back in 1998 by Carlo Strozzi. But here's the twist: his Strozzi NoSQL database was actually a relational database. His rebellion was not against the relational model itself, but against the complex SQL interface. He wanted something simple that fit the Unix philosophy. It was a historical footnote. The term was reborn in 2009 with a completely different meaning. Web 2.0 giants like Google, Amazon, and Facebook were facing an architectural crisis. They were generating data at a volume, velocity, and variety that traditional, single-server databases just couldn't handle. They needed a new kind of database zone that was distributed, non-relational, and could scale out across thousands of cheap servers. This new movement was about architecture, not interfaces. But as it matured, the aggressive NoSQL softened into the more pragmatic, not only SQL. This acknowledges that NoSQL and SQL systems often live side by side in what's called polyglot persistence. The choice isn't SQL or NoSQL, it's about using the right tool for the right job. Part 2: The Great Divide SQL vs. NoSQL. So what are the core differences? Let's break it down into 4 key areas. First, data structure and schema. SQL databases use a rigid, predefined schema. You define your tables, your columns, and your data types upfront. It's like building with perfectly uniform Lego bricks, strong and predictable. NoSQL databases have flexible schemas. A document database, for example, lets you store data in JSON-like documents where each document can have a different structure. This is often called schema on-read. The structure is determined by your application when it writes the data. It's like building with Play-Doh, flexible and easy to change. Second is scalability. This is a huge one. Traditional SQL databases were designed to scale up. To handle more load, you buy a bigger, more powerful, and much more expensive server. You're limited by how big a single machine can get. NoSQL databases are designed to scale out. They distribute data across a cluster of commodity servers. Need more capacity? You just add another cheap server to the cluster. This is how they achieve massive, web-scale performance cost-effectively. Third, consistency. SQL databases are famous for their ACID guarantees in atomicity, consistency, isolation, and durability. This ensures that transactions are processed reliably. It's an all-or-nothing promise, which is critical for things like financial systems. Your bank transfer either happens completely or not at all. Many NoSQL databases trade strict ACID guarantees for a model called BASE. Basically available, soft state, and eventually consistent. BASE prioritizes availability. It says the system will always be available to respond, but the data you read might be slightly out of date for a moment as updates propagate through the cluster. It will eventually become consistent. For a social media feed, seeing like appear a few milliseconds late is an acceptable trade-off for the system always being online. Fourth, querying. The language of SQL as well. SQL. It's a powerful, standardized language that excels at complex queries and, crucially, join that combine data from multiple tables. NoSQL has no single standard. Each database has its own API or query language. Queries are often simpler and complex join are usually avoided. Instead, data is often denormalized, meaning related data is stored together in a single document to optimize for fast reads. Part 3: The CAP Theorem. Now, why did NoSQL systems make that trade-off between consistency and availability? The answer lies in one of the most important principles in distributed systems, the CAP Theorem. Conceived by Eric Brewer, it states that a distributed database can only provide two of these three guarantees simultaneously: consistency, availability, and partition tolerance. Consistency C means every read gets the most recent write. All nodes see the same data at the same time. Availability means every request gets a response, even if it's not the most up-to-date data. The system is always on. Partition tolerance P means the system keeps working even if the network breaks down and nodes can't communicate with each other. Here's the kicker: in any real-world distributed system, network failures partitions are a fact of life. You must tolerate them. So P is not optional. This forces a direct trade-off. When a network partition happens, you must choose: do you sacrifice consistency or availability? CP systems consistent and partition tolerant choose consistency. If a node can't confirm it has the latest data from its peers, it will return an error or timeout. It refuses to serve stale data. Think of a banking system, but to show an error, then the wrong account balance. AP systems available and partition tolerant choose availability. Every node keeps serving requests with the best data it has. An e-commerce site might choose this: it's better to let people keep adding items to their cart, even if the inventory count is temporarily out of sync across data centers. The CAP theorem provides the fundamental why behind the architecture of most large-scale NoSQL databases. Part 4: Taxonomy of NoSQL models. NoSQL isn't one thing. It's a family of different databases, each optimized for a specific job. Let's look at the four main types. First, upper key value stores. This is the simplest NoSQL model. Think of it like a giant dictionary or code check. You have a unique key, and you use it to store and retrieve a value. That value can be anything: a string, a number, a JSON object, even an image. The database doesn't care what's inside. Their strength is pure speed. Because it's a direct lookup, reads and writes are incredibly fast. This makes them perfect for caching, where you store frequently accessed data in memory to speed up a slower main database. They are also used for managing user sessions on large websites and for real-time applications like gaming leaderboards. Redis and Amazon DynamoDB are famous examples. Next, document databases. These evolve the key value concept. Here, the value is a structured document, typically in JSON or BSON format. Think of a document as a self-contained folder of information that maps naturally to objects in your application code. Their killer features are schema flexibility and rich querying. You can filter and search based on any field inside the document, and you can add secondary indexes to make those queries fast. This makes them a fantastic general-purpose database and a favorite for developers. They are perfect for content management systems, e-commerce catalogs with varied products, and storing complete user profiles. MongoDB is the undisputed king of this category. Third are Tor wide column stores. Don't let the name confuse you with relational tables. Data is stored in what looks like rows and columns, but with a massive twist. Each row can have a different set of columns, and you can add new columns at any time. They are built for massive scale and extremely high write throughput. Their architecture makes them incredibly good at ingesting enormous streams of data. This is why they are the workhorses for Internet of Things IoT applications, handling data from millions of sensors. They are also used for large-scale logging, event sourcing, and real-time analytics. Apache Cassandra, used by Netflix and Instagram, is a prime example. Finally, my personal favorite are graph databases. These databases are purpose-built for one thing: understanding relationships. The data model has nodes the entities, like people or products, and edges the relationships that connect them, like friend of or purchased. The magic is that these relationships are stored as first-class citizens. Traversing from one node to another is an incredibly fast operation. This makes them orders of magnitude faster than a relational join for complex relationship queries. They are perfect for social networks, powering recommendation engines. Customers who bought this also bought and, crucially, for fraud detection. By modeling accounts, devices, and transactions as a graph, analysts can find sophisticated fraud rings that would be invisible in any other database. Neo4j is the leader here. Part 5 of the future of NoSQL. The NoSQL landscape isn't standing still. 3 key trends are shaping its future. First, the rise of multi-model databases. Instead of using 3 different databases for your app polyglot persistence, a multi-model database offers document, graph, and key-value models all in one engine, with one query language. This aims to give you the flexibility without the operational headache. Second, the impact of serverless. Serverless NoSQL, like Amazon DynamoDB or MongoDB Atlas Serverless, completely abstracts away the infrastructure. The database scales up and down automatically in response to your traffic, and you pay only for the reads, writes, and storage you actually use. It's a game changer for reducing operational burden and cost, especially for applications with spiky traffic. And third, deep integration with AI and machine learning. NoSQL databases are the perfect place to store the vast amounts of unstructured data needed to train AI models. More recently, with the rise of generative AI, they've become critical for vector search. They act as the long-term memory for AI applications, storing data embeddings that allow an AI to find the most relevant information to answer a prompt. This is a massive new frontier. Conclusion: so, is SQL dead? Absolutely not. The era of a one-size-fits-all database is simply over. The great lesson of the NoSQL movement is that we now live in a rich ecosystem of specialized tools. Relational databases remain the best choice for transactions and complex queries on structured data. NoSQL databases provide the scale, flexibility, and performance required by the massive, fast-moving data that powers our modern digital world. Expertise today isn't about picking a side. It's about understanding the trade-offs and having the wisdom to select, combine, and optimize the right. If you got value out of this deep dive, hit that like button and subscribe for more content like this. If you're ready to put your NoSQL skills to the test and see how much you've really absorbed, I've got something perfect for you. Head over to mindhustle.net and sign up for our NoSQL skill assessment. Click the link in the description, sign up at mindhustle.net, and let's see what you're made of. Your NoSQL journey doesn't end here, it's just getting started. And also let me know in the comments what's your favorite NoSQL database and what do you use it for. Thanks for watching.